What did you vote? Yes.
Okay, we should start. Good. So basically, nice to see you again after the long Easter break. I just come from a 9 to 2 administrative meeting, so I'm completely brain fried. So let me know if I start ranting against this and that policy of the university. Where are we? So we are towards the end of our module on Bayesian models of cognition implemented with Bayesian tools. In the first lecture of this module, we discussed Bayes' theorem as a model for cognition, has applied to perception, has applied to decision-making, to social cognition, learning, blah, blah, blah. And we went from the general model of the simple and weighted Bayes' theorem to a variety of experimental application, and we started implementing them. In the lecture last week that Peter was so nice to come and give, you were introduced to a Bayesian multi-level reinforcement learning algorithm. Though I know that he defines reinforcement learning as a bad approximation of the hierarchical Gaussian filter, where multi-level doesn't mean, as we usually did, that we have a parameter that has a value for, let's say, individuals and a value for the population, but a model in which the different aspects of the quantity that we're trying to estimate in the environment are parameterized in hierarchical fashion, where there is a mean and a standard deviation, an estimate of the change of mean over time and the standard deviation of that, potentially an estimate of the change of mean over time and the standard deviation of that, potentially an estimate of the change in the standard deviation over time, blah, 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 right? I know that he prepared some stuff in Julia, but I also dug up implementation of a 2-level HGF in Stan and R. If you're interested, I'm not going to cover that today, at least that wasn't the plan, but I can share it so you can have a look at how it would be in a more familiar framework. And I checked it still works. We also tried to implement it as a 3 or full so that it estimates on its own how many levels it is. And the amount of divergences would fill your nights with dread and nightmares. Okay. What I want to do today is I want to start with questions. If you have questions on either the first part of the Bayesian cognition or the lecture from last week that yesterday I actually watched and commented to Peter, I can answer your questions if I understand them. And then what we will do is we will try a bit of free jazz on the weighted Bayes model. Now, as I will present a few different scenarios, and I will show you how I would go adjusting the model to these scenarios. Stuff like, what if we actually model that the 8 marbles that you sampled, are not a pointwise log odds, but are actually an underlying theta distribution. So you're trying to estimate the underlying distribution of red and green in the urn. What if instead of having a trial by trial setup where you get a new earn in every trial, you actually keep updating your estimates on a trial by trial base. What if you are also estimating how credible the other person is as a source of information? Blah, blah, blah. We'll see a few of them. Because I think even if you shouldn't just use weighted Bayes because you know it in any context, it's a useful exercise to think how to change the structure of the model to fit with different ideas, right? To get you a feeling for how we build these models. And possibly today, depending on how fast we go, we will start the next module. That is, I will get you to play, call it computer game is a bit exaggerated, but experimental paradigms, in which you will have to explore the outer space and figure out which of the aliens will try to kill you and which you can exploit as a good colonialist. And then we will do the same exercise that we did with the matching pennies, plausibly from next week, of building models that are at least partially theory-driven, but of how you are solving that task. Good. So questions, right? They can be on Bayesian models of cognition, on the AGF, on what the heck we're doing in this course, or on why. No questions? Everything is clear?
No.
Yes.
Just do a portfolio, like, will we have time to work on the current portfolio on this?
Tomorrow. Yes.
Right.
Yes. Okay. Yes. So this is just because I want to stick some stuff in the rest of the course, add some stuff. So I see if I can anticipate the categories that experiment today. Otherwise, we'll do it next week. That's me. There was something else that wasn't clear. Somebody says no from that.
No, I don't know. I don't have any specific questions, but I don't think everything is true. Yeah. But yeah.
Okay, but are you having a good feeling for, let's say, what the weighted Bayes model is doing? Right? Do you have a good feeling or initial conceptual grasp of what the hierarchical Gaussian filter is and how it fits in these sort of ideas of Bayesian models of cognition?
No.
Nope. Good. Yes. So the general idea in the AGF is that you are trying to estimate something in the environment, right? Which in our case, it could be the distribution of red and green in the urn. And it's trying to say that there is an underlying process, which depending on how many levels it has, might have a mean and a standard deviation, or might have a mean and a standard deviation, which are generated by a Gaussian walk that changes over time. Right? It takes a prior, and it takes what it gets from the environment, and what it gets from the environment becomes the prior for the next trial. So in that sense, it's integrating two sources of information, as we've seen in the previous examples, except that one, after the first trial, is the posterior of the previous step. And we'll see how to transform the weighted Bayes to do that. Did you have a, sorry, I was, yes, just read myself. Good, yeah. It's a model that has been appreciated a lot because it basically built on one of the pillars of computational psychiatry, mathematical psychology, which is reinforcement learning. which is a really neat algorithm. But it does so in a way that can better deal with changes over time. First. Second, because it can be mapped onto some promising theories of how cognition, or according to some authors, even the actual cortical structure works. And there's a few fMRI, as far as I know, only fMRI studies that actually try to map changes in these different parameters, right, from the mean to the volatility to whatever, onto specific brain regions, activations. What was the question there?
It's just like understanding the hierarchical part of it.
Yes.
Is the hierarchical part the thing with like more layers happening simultaneously in terms of like the last trial, whatever, the last posterior becomes the new prior? Is that the hierarchical, or is it just the lag thing mechanism there?
Well, so the idea is that these mean, so the mean of whatever you're estimating out there, I don't know how many berries there are going to be in that bush, and can be what you're trying to estimate, or can it actually be the expression of a yet underlying, actually I can't remember how they spell it, but let's say change in mu. So if you take change in mu and the previous mu together, they will give you the current mu. So it's not just about what you're getting from the environment, it's also about what the previous mean was and how much you can expect it to change. And since a different, let's say, keeping the bush and berries stupid metaphor, right? At different periods of the year, these mean will change with different speed, right? So you might also have, and now I'm going to say it's the second derivative because I cannot do the two hats, right? A change in the change of mu. This is the hierarchy. Now, there are people who can make it work, but all my attempts at making anything work beyond 2 levels fail terribly. The second thing that I should mention, which might make, well, I think actually Peter did a good job at telling that, is that this is a Bayesian model of how cognition works, which doesn't do what Markov chain Monte Carlo is doing. Doesn't do the full sampling, but it's using some tricks, variational approximation, variational Bayes, to actually make it happen in really fast times. So by making assumptions that we know in advance the shape of the posterior, the distribution of the posterior, we can approximate what the posterior would be if this is the prior, this is the information, and that's the shape of the posterior. Variational inference is a really useful tool. It has one big issue, that is we never know if it's true. On the good side, it might actually be a good model of what the brain does, because the brain needs to work in real time. So it might be willing to pay the price of making a few mistakes. Gelman, who's one of the founding fathers of STAN, has been very frustrated with it and how fast it was spreading like a wildfire in the literature. And he has been pushing for, and I can't remember how much directly involved, but in an alternative algorithm that's called Pathfinder, which is supposed to at least be more transparent in its failures, like good old STAN tradition, right? We're not right, but we tell you that we're wrong all the time, right? And Pathfinder is actually a really interesting development because it allows to, for instance, do estimations in real time as we're running experiments. We can approximate a solution of what we think that the learning rate is, for instance, and predict which kind of stimuli we should show the participants in order to maximize the information that we can gain, right? If we want to reduce the uncertainty maximally in the learning rate, right? Which of these set of stimuli should we show to this participant? The work is still ongoing on these stuff, but it opens up really exciting possibilities. Yes.
It's a bit more like detailed question, and maybe what is it?
Yes.
But it's, am I understanding it correctly when the parameter that kind of is for the volatility, like the updating?
Yes.
I'm kind of visualizing it as a learning rate a little bit, or like a step. It's like reminding me of something that's updated. It's just the thing that I want to ask about is it's constant. It's not dynamic. So the step that it's changing or like updating with is constant.
Oh, it depends on how many layers there are. If you have 2 layers, it's constant. If you have 3 layers, it can change with a higher. Yeah. Malte?
And one more difference, reinforcement learning, when you have the prediction error, and when you have a learning rate, then the change is deterministic. You have everything you need to know. Right. But in this model, it's not deterministic. The position in the level above is not saying you're going this far in one direction, it's saying you are sampling from a distribution that's this wide. So the learning rate in itself is
Not constant, it's the same.
It's a distribution. Yeah.
There's not even a value from the distribution, it's just the whole distribution.
Yes.
all parameters.
Yeah.
Yes, that is true. Sorry, that was a.
You said it, so if, for example, you want to simulate some data using the ACM, you do set the volatility parameter per each layer. So
Yes.
you can tell if your first layer is going to have whatever, -10,
Yeah.
the next one's going to have -30,
Yes.
depending on how much volatility you expect in the environment.
Yeah, so you could in principle say that it's a distribution and at every trial you sample from that distribution.
Yeah.
What the parameter value would be to sample from that distribution what the produced observable U will be.
But like if you have in reinforcement learning, if you know the next 5 trials and you have the learning rate and you know they're all going, then you know exactly in which trials are they going up and which trials are they going down.
Yeah.
I don't think that's not my understanding. You can do that in the HDF. You predict one trial with distribution that's somewhat wide, and then you see where it went, and then you go from there. And
Yeah, so the idea is that it's a Gaussian walk, meaning that the change will be sampled from a distribution that is centered at 0. So it can go both directions.
it's conceptually the same, but the process is like
Yeah.
Some complex stuff we're doing.
Yes. And there's also a reason for which, so with what we do in the course, then you can go and tackle the AGF and make it work for you. But we don't start from that because we want to have a more intuitive understanding of what happens when we change these specific wheel, right? Good. But it's nice to have a glimpse at what it is about, and you'll have the code. It's not that complex if you want to play with it. Yes.
I have a question, completely different topic.
Good.
Is that okay?
Yes.
It's about real parameterization.
Ooh. Yes.
Okay. So once upon a time, you and Melle had a discussion on whether to put the transformed or the not transformed parameter in the parameters chunk upstream.
Yes.
Remember I discussed in which order it
Yes.
has to go. And I can't remember what we decided, but could it be that it works if you do it like either way?
So I think that there's the more intuitive way is that you have the transformed version in the parameters. I think
you could also say it's more intuitive to have the transform one in the transform.
Well, so the point is,
Nice.
it's you're putting so the one that you're defining in the parameters is the one we should put the prior.
Okay.
So it's the parameters on which you're putting the prior. And since we want to put a prior on a distribution that is unbound, then that's why we tend to put it in the parameter channel. Because then we can use, if you're me, right, a normal center at 0 with a standard deviation of, depending on the problem, right? Let's say 1 or 0.5. And then you can estimate that parameter in a completely unbound way so that the Hamiltonian Monte Carlo is happy. The Queen Mobile can just drive all over the place without bumping it against anything. And then we transform.
Right.
That's where it's most intuitive.
Yeah, that makes sense. So if you put prior, I mean, if you write like target is updated by this probability density thing.
Yeah.
If you then put a value that was, or parameter that was from the transform parameters in there, I'm just actually messing staying.
I do have an answer. I tried to do that once, and I went on the mailing list and I found out that it was dangerous territory.
Okay.
Yeah, I think you can technically do
You
it.
can technically do it, but you have to do a bunch of math on your own that otherwise Stan does for you automatically. So Stan works by the derivatives.
Yes.
And so when you do the transformation, Stan automatically figures out what's the derivative of the transformation. And it's set up to do that one way from parameters to transform parameters. If you do it the other way around, if you put a prior on something in transform parameters, then you have to compute something, and I had to.
So the Jacobian something, right?
Jacobian
Yeah.
adjustment or something, which is like a multi-dimensional differential equation. I spent like 2 days finding out what it even was, and I didn't manage to find a solution to it. I just figured out I had to do it. So that's
Yeah. Well, but you can, right?
Okay, so hypothetically, if I did do that, and I got results that were very, very similar to what I got out of doing it the correct way,
Yep.
then I just got lucky.
yes.
Yes, and you can send me the script and I can check if I spot any issue, but you can, it's technically possible to do. It's just that there are easier way of doing things and harder ways, yeah. Yes?
A different topic again. So I understand why hierarchical Gaussian filters are Bayesian models of cognition.
Yes.
But the model you introduced 2 lectures ago about predicting the rate of red model.
Yeah.
Where was the Bayesian in that? What that, because that was in a Bayesian model. I mean, I think that's how it was.
It is a Bayesian model, yes.
Yeah.
Because it can, so it takes the Bayes theorem as a way of combining 2 sources of information or more, where traditionally one source is the prior and the other is the latter.
Yeah.
But the math doesn't care. So you can use it to combine 2 external sources. But today, we're gonna see, because it's slightly more involved, today we're gonna extend it so it actually estimates underlying distributions of rates instead of doing the logouts pointwise transformation. Right, so where we turn 1 out of n out of 8 red marbles into a number of logout scales, right? So we shrunk it to 0 to 1 and then did the logouts transformation, so we could sum it up with whatever we got from the other source of information. Now we're going to do the next step and say, what if we actually took it seriously and says, if I sample 3 red marbles out of an urn, out of 8, right? That gives different probabilities to different rates. So I can actually estimate the full probability distribution for the underlying rate of red compared to green. Right, that would be closer to the generative part of the AGF. And then we're gonna do it temporally. So what if you keep on sampling? How do you combine the new sampling with what you inferred in the previous trial? Right? And then it would be closer to this idea of prior and likely. But the AGF can be just as well adjusted to 2 or n sources of information setups. Right, where this mu is not just generating one observation, but it might be generating both your sampling, the self, but also what the other is sampling, and therefore their choice that we can observe. And then what we're doing is we're trying to go from these here. Right, it's exactly the same setup, just we are using simplified mathematics, right? We are assuming that the underlying measure doesn't change over time. We're just trying to estimate it. And therefore, we don't need this whole paraphernalia up here. Does that make sense? So take the weighted base that we've used, right? And say, actually, the rate of red marbles in the urn will change over time because there's a maleficent demon in the urn that keeps changing on things to mess up with you, right? Or because you're sampling from going out in the woods and foraging, right? And then we could start building actually the AGF from our weighted base model. But in order for the model to actually be able to solve the problem, we would need to implement the variational base. We would probably need to implement the variational base because it gets too complex to be solved with information available. So we need to make some approximations. And that's really what Chris Mattis was doing in his PhD thesis. Does that make sense? Also, I added Peter's lecture to the YouTube channel, so you can go back and check it again. I got his permission. Good. Were there more questions? Sorry. So recap, Bayes' theorem is a way to optimally combine information from multiple sources. I put optimally into parentheses because I'm always skeptical of optimality things. It's taking at face value the information contained in the different sources of information, which we know in real context might not be optimal, right? If somebody is trying to cheat us, right? Or if somebody is terrible at estimating rates from sampling from an urn, we might want to downweight that information. Simple Bayes is a face value optimality versus weighted Bayes as a more nuanced perspective. We've seen and spent a lot of time with the logit link as a gateway to make things simpler, right? We've seen that we can just sum up the information contained in the different sources if it's on a log odd scale, right? We don't need to renormalize it. It's doing it for us. And we've seen, in a certain sense, what is meant by nested models in cognitive modeling or computational modeling in general, which I'm not sure I've put those words on those. So I'm actually going to spend a few minutes telling you what does it mean to have a nested model. The idea is that we have seen that my initial formulation of the simple Bayes would assume that we are modeling an underlying probability that the next, or an underlying probability that I should choose red in the next try. Right? Meaning that if one of my sources was 2 out of 3 red marbles, and the other source was 2 out of 3 people telling me to pick a red, right? I would sum them up on a log-out scale. I would inverse logit the solution, and I would get 0.8. Right? So I see more marbles, more red marbles in my hand. More of you than not tell me to pick a red marble. I increase my chance of saying that the next marble is going to be red. But that conflicts with another way of conceptualizing the problem, which is actually we're trying to estimate the underlying probability that the next marble is going to be red. Not whether I should bet on red, but actually what's the probability that the next ball is going to be red. Does that make sense? And I sent an email and discussed with a few of you, but just want to bring it up again, right? If we have that conceptualization of the process, right? What we do is we actually do a mean between the two. Right, so we put a 0.5 weight on both of them. Right, if there were 3 sources, we would put a 0.3333333 weights in front of each of them. Right?
Is that single base or weighted base?
Well, so now because the weighted base is estimated. So it's saying they're potentially different weights. We're going to say, if we take the simple base as simply a way of optimally combining the information from the 2 sources with a fixed weight in order to reconstruct the underlying probability, this is how we would express it. But your question is pointing to something important we shall bring up in the next bullet point. So what we do now is we say that if we put 0.5 times 66 plus 0.5 times 66, actually summing them up, we get 0.66. And here I sort of cheated. It should be 0.5 times logit of 0.66, blah, 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 but that's the results. That's the same thing. Right. So now we have 2 different ways of conceptualizing the simple base. We should pick, of course, the one that makes sense given the way that we frame the experiment, but we're not always that careful, and we might have different participants that interpret the problem in different ways. How do we solve this? Well, as you were saying, if we conceptualize the problem as a generic weighted base where we don't specify the weights, right, we can estimate what participants are doing, and we can see whether there are participants that are doing something like this, the 0.5 weighting, or participants that are using the first simple base, which has a weight of 1. In that sense, both of the versions of the simple base are nested within the weighted base, meaning that if we trust that our weighted base is a sensible model, we might not even need to run the simple base versions because the model would tell us whether participants are very similar to those. Just like a reinforcement learning model would tell us whether participants are adopting a strategy that is very close to win-state ratio. Yes.
And maybe you said it, but so we were just confused yesterday working on the portfolio because if you do the first one and
Yes.
you say that each one has a weight of 1, then
Yes.
you can get a rating that's above 8. If you do the conversion to a continuous scale, right?
Yes, if you're in a Gaussian, for instance.
Yes.
Yes.
And that doesn't really make sense because that doesn't follow the data.
Yes, exactly.
So what we aimed for doing instead was to constrain one of the weights to rely on the other weight, that they would never go above one in
Yes,
total, right?
Yeah.
But in what you're saying here is that it's also okay to. I'm not following why that would be like a good idea to have a model that could go above.
Oh, so then again, there are different ways of respecting the boundaries,
Yes.
right? So now you implemented it with a Gaussian outcome.
Yeah.
Which means it can in principle go to infinity. But as I'll show you in the next few slides, you could conceptualize that as an aggregated binomial. How many ones out of 8, right? How high the score goes when trusting a person. And if you use that conceptualization, then when you sum up the log odds of the two sources of information, no matter how high you go, then you need to convert that into a rate between 0 and 1, which is then applied to the 8 trials, the 8 possible sequence of ones. And then automatically it respects the boundary, right? So you're right. If you have implemented a different likelihood, then you might want to enforce the boundary by constraining the weights to sum up to 1.
But it doesn't really matter if you do zero between 0.
exactly. It solves the problem for you, right? And it has different pros and different cons than the other charts. Just one additional point. You are bringing one conceptual assumption into the problem by saying that they sum up to 1. That is, if you trust more the other, you trust less your own. And vice versa, because what you might be is a terrible learner, right? You sample, you have no idea what's the underlying rate. You look at the other, you don't trust them, and then you pick at random. By making the weights summing up to 1, you're sort of saying that's not a likely scenario, right? Because if you don't trust the other, you trust your own judgment. If you don't trust your own judgment, you must trust the other because they have to sum up to 1, right? And that might be fine, right? There are contexts in which it's fine. It's just a question of being aware of which assumptions you're putting in the model. Yes.
But wouldn't this, I mean, this is just, as I understand it, would just be a reprioritization, like, so, I mean, you still have to make a decision in the end, right? And
Yeah.
so if you have this sort of dual model where you have a weight for yourself, but also for the other, then, I mean, you have to make a decision, and that's in the, I guess, the softmax somewhere, or.
Well, so here we're not using, we're using
Logic, but that's the same as the softmax, if you have just a.
Yeah, we just don't have the inverse temperature parameter.
My point is just that, you can have one parameter for each, source.
Yes.
Or you can have a parameter for the relative strength.
Yeah.
And multiplication afterwards.
Yeah, which would be the
same.
equivalent of the temperature parameter. Right?
Yeah, exactly.
Yeah.
So that would
Yeah.
achieve the same thing essentially.
Yes.
So the conceptualization is the same.
Yes.
Parameterization is different.
Exactly. The reason for which I find the first parameterization, so independent weights, more intuitive is that because I can look at them and say, well, the first source is not really determining my choices, and the second source is also not really determining choices. While otherwise, I would see that there is an imbalance, maybe, right? But then the temperature is such that all choices are chance. But I would be able to retrieve it as just by at first look. It's just a question of what I find intuitive to look at in the output. In the output. Yeah.
I'm just wondering, like, if you have the scenario explained where you have none of the sources are explaining your outcome.
Yeah.
That would just translate into a high variance
Yes.
in the normal budget normal
Yes.
at the end, right?
So you would have that the weights tend to be close to 0 in log out scale and quite uncertain. Yeah. But you're right. So mathematically, the two are equivalent. It's just a question of do I want to directly interpret the weights, or do I want to have to think a bit more? And in certain cases, having to think a bit more is the right choice. In others, I might want to just look at the coefficients. Good. So I'm gonna use this, but all that I say is, so this experimental power line, but all that I say can be converted to your portfolio assignment. What we are gonna do before the break is we are taking the information sources as point-wise numbers, right? Because I didn't want to make your life a mess from the very start. Is this a realistic representation of the process? So actually, from a cognitive perspective, I have no idea. Proper Bayesian theorists of the mind, they would say no. Right? We always work with distributions. Right? I might think, well, actually, people might be simpler than that. But we want to know how to do that. So I'll actually see that later. So how should we model information sources in order not to take them as point-wise numbers, but actually to take into account the uncertainty that is involved in interpreting those sources, right? Because in principle, we might have an urn with 1,000 marbles, and by chance, the only 8 red marbles ended up at the top, right? So even if we sample 8 marbles out of 8 that are red, there is still a small chance that the true underlying rate is actually more in favor of green. Yes?
What do you mean point-wise?
So in the way that,
Discrete numbers.
yeah, and in terms, it's not discrete, but so what we were saying is that we have a number from 1 to 7. What was that? Or 1 to 7, yes? I think it doesn't go all the way up to 8, right? But it could be in principle from 0 to 8, right?
From 0 to 7.
No, I think in the Gumball's experiment, it's 1 to 7, yeah. And so 1 to 7, and then what we did is we did a transformation, which now, what was it? Was it +1 divided 9, something like that? Can you remember? You have it on the slides? I can't remember the exact one, but let's say it was +1 divided, or it could be simply divided, actually it could be just divided 8, which gives us a sequence of numbers that goes from 1/8 to 7/8. And then we did logit of those, right? Which means that when you observe, let's say, 2 red marbles out of 8, you do this operation, it becomes 1/4, which is 0.25. And if we do logit of that, we get something like -2, something like that. I don't know, I can't remember. But, and then we say, if we want to predict whether the participant will say that the next marble is more likely to be red, then we do our old y as a function of, you know, weight for the source of information from my own sampling times -2, right? Then we do the same for the others. And let's say that there's only 2 out of 4 that say it's red. So we can say 0, right? So we are conceptualizing the information contained in my own sampling, 2 out of 8 red marbles. And in the 4 others where only 2 are saying red, as single numbers. Does that make sense?
No, sorry, what is a single number?
-2,
Okay.
right? We take the hand with 3, 6, 7, 8, and 2 are red, and we turn that into a single number.
Okay. Yes.
But these actually is a richer form of information, right? We can say this is actually an aggregated binomial. So it's a sequence of independent sampling from the urn. And we can try to reconstruct the actual distribution of possible rates below that. So we can say, let's take all the possible rates of red between 0 and 1. Say if we run this 10,000 times, how many times do we get 0? So do we get 2 red marbles when the rate is actually 0? This is going to be 0, right? Then we can try with all the possible rates, right? And we're going to get a distribution which is going to be something like this, right? A peak in the low rate, but a long tail, right? If we had sampled 14, right, we might have a much more peaky distribution. If we had sampled 3, we might have a much more broad distribution. Does that make sense? And so by reducing this sampling to only one number, we're losing the information contained in the distribution. Does that make sense? Good. So what we're going to do after the break is seeing how we can tell Stan that we should actually extract that distribution from the hand with the marbles and not just do our hacky simplifying of turning these into a number. Let's take 10 minutes.
I think it's more. Yeah, if my notes say something.
Yeah,
like
okay.
this,
From the ratio.
It's only for the house.
Not only like, but they are different. So you know. But this time.
Det er måske fordi han gør smør.
It's also like.
Hvor meget energi på at lave noget materiale til dem også, men det er sådan også mega uretfærdigt, når man kun laver noget for dem, der ikke men de gør det i det er helt jeg siger også til lige en gang, det kan komme og være sådan, jeg har med fri, jeg synes det er godt svært med, og hver gang jeg møder svært, så er det og 18 gange 9, eller 18 gange 9, ikke giver.
Yes.
Yes, sorry, Luke. So I was just saying that we are modeling both the self and the other as aggregated binomial. For the self sampling 8 marbles, we have an aggregated binomial out of 8 trials. For the other, which has 4 possible phases, right? So green with high confidence, green with low confidence, red with low confidence, red with high confidence. We can model it as an aggregated binomial with 3 trials, going from 0 to 3 once, getting out of those. And this is how we can model it, right? We are now imputing the sources as integers, right? The amount of ones, if you want, the amount of successes in the binomial. In the data, we provide how many rows there are in our data set. We provide the y that is for each trial. What is the participant choosing? Red or green, red being 1 and green being 0. Then we have an array of integers that says out of the 8 marbles, how many of those were red at any given trial. And then we have a second array of integers of length n, in which we have in these scale from 0 to 3, what was the score of the other, the evidence that the other is providing in terms of red. Does that make sense? Then we have our usual parameters. We have a bias. We have a weight for the first source. We have a weight for the second source. But now we also have estimated rates underlying the integers that we have in source 1, that's theta 1, and the array of estimated rates that underlying the integers in source 2. Right? So we're creating a place where we can save those distributions that we can infer underlying 2 red marbles out of 8 marbles, right? And then we have a model in which we put a prior on our bias, on our first weight, and on our second weight. Nothing new. But then what we tell is that actually before estimating the probability of picking red in the participant, we take source 1, we say that it's out of 8 possible marbles, and that source 1 number is generated by an underlying theta 1. Right, so we respect the usual formula. We say there is a distribution which has an outcome and underlying parameters. But now we know the outcome and one of the parameters, and we're asking Stan to estimate the underlying rate. Why are we doing that? Well, it is deterministic, right? But it's the most convenient way of doing that, right? Instead of having to feed long vectors of probability distributions to Stan. We do the same for source 2, and here I made a mistake. It should be 3, not 4. And we ask it to estimate theta 2. That means that for each of the value in source 1, Stan will estimate a distribution of theta 1s. At every row, a different distribution. For every value of source 2, Stan will estimate an underlying rate, right? A distribution, a full distribution for each number in source 2. And then we say that the y, the choice, is produced by equation that says, as we've done before, bias plus weight 1. But instead of saying weight 1 times source 1, we say times theta. And I have to admit, I don't understand the underlying logic, but times only takes vectors, it doesn't take arrays. There is an explanation. I look it up every year. I forget it every year. We just tell it, take the array and transform it into a vector. Plus weight 2 times the theta 2 transform into a vector. Does that make sense? So we're replacing source 1 and source 2 with the theta that we estimated in the line immediately before. Does that make sense? Yes.
Not really.
What's puzzling you?
Where you this way estimate data 1 and 2,
Yes.
are those the priors?
There is a fantastic talk by Richard McInerney that came out a couple of days ago, which is, I can't remember the exact title, but the key message is, how do we teach Bayesian statistics without frequentist terms? And he claims in that talk that there is no distinction between prior and likelihood exactly because of things like that.
Right.
But no, this is actually, it's saying, given that we know source 1 and we know 8, estimate theta. It's the only parameter, because the idea is that we have this general form, and thanks to Bayes, we can just put in whatever we have, and Bayes will estimate whatever we don't have. So, sorry, Pernille.
No, you're fine. Totally fine. Delete it.
So basically, I'll say here it's 2, right? And then it's out of 8 with a theta of 1. Okay, 2 out of 8, right? What is actually the distribution of rates that, or the probability of each possible value of rate that would generate this? And then it does this thing. And let's say that in this model, we're sampling 3,000 times, right? So we have 2 chains, and after the warm up, each chain has 1,500 samples, iterations, right? It's gonna give us 3,000 values that represent this distribution. Then we have the other one, which is, I don't know, 3 out of 3. And we need to estimate theta 2. Right, and that's going to be something like this. For the people on the Zoom, I just represented a distribution between 0 and 1, probability distribution between 0 and 1, which is heavily skewed towards 1. Now, what we can do is, if we put these numbers between 0 and 1, each of the samples will have a number between 0 and 1, a value between 0 and 1. We can work on a logic scale, and you cannot see here, but it says we need binomial logic, right? The theta is estimated on a logic scale, which is the equivalent of taking these values and making a logic transformation of them. And then we can say, oh, there's bias. There's W1 times the evidence from source 1. There's W2 times the evidence from source 2. But instead of putting the pointwise value that we had before, we can actually put the full theta 1. And after W2, we can put the full theta 2. Right? We're not reducing the uncertainty by creating artificially this one point that represent the evidence on this logout scale. But we are taking the full distribution and every sample that we have of that, we'll put in here. And yes, that way we are propagating the uncertainty. Like we're keeping all the information, which in other words is we're propagating the uncertainty. We're not, before we would have been time-wise certain that it was this one value. But now we're actually saying it could also have been this value, this value, this value, but just less likely. Ingrid?
So I totally get the logic of, keeping all the information
Yes.
there, and if I were to teach a machine to do these tasks, that's definitely what I would do, right? But if the goal is to estimate how people do it, then the merit of this approach should come from the idea that people actually take into account the number of marbles. So it might be, my point is, it might be the case that it doesn't really matter much to people if you see 2 out of 8 or 200 out of 800, that they might judge this information, more or less in the same way.
Yes. So I don't know if people on the Zoom heard it properly, but the question slightly rephrased is this is a beautiful procedure if a machine had to do the exact combination of the information containing the two sources, but if we're talking about people, are people really doing this process? Right? Does it make sense to assume that people are doing this process? Correct? And that's a bit the point that I was raising a bit earlier, right? That the fully Bayesian evangelists, they would say everything in cognition is Bayes, therefore we need to do this. And in a certain sense, also a lot of the HGF implementations are doing this. I'm not sure whether people are actually. One way that we could go, a pragmatic way, would be if we could make sure that in the data, right, we always feed the integer and we do the pointwise transformation. Would it work? I'm wondering whether we could actually implement the two models and then do model comparison.
So what would be the second model?
One model in which in some transform data here, we are transforming source 1 and source 2 into the pointwise estimates that we did before, right? Divided 8, then on a log scale. And then estimate the model. And in the second model, instead, we're doing this full uncertainty propagation.
I'm actually more worried about this trick with the social information, because of like the coding it as 1, 2, or 3 of 3 is also very arbitrary, right? So at the very least, I would put a parameter for the amount, like the amount of marbles that you interpret very short to mean, or the total amount of marbles.
And that's not captured by the weight?
No, because of the 4, essentially the 4 that you put in the second to last line is, I mean, that could be a parameter as well, right?
Oh yeah, that's actually true. Yeah.
Or maybe the.
But it wouldn't be the optimal. You could make it into a parameter, but it wouldn't be the optimal parameter.
I'm just saying, like, if I, get this social information, I might not interpret it as 3 out of 3, but I might interpret it as 100 out of 100.
Yes. Okay. So absolutely.
Yeah,
So
that will go into the weight, I guess.
the question is this aggregated binomial the best way of representing source 2? And we can debate that.
Yeah.
Right? Now it's more for showing you how to do this sort of operation. There was a question, Clara? Yeah.
Yeah, there was this clarification. So when you try to do you estimate data, then you estimate on each kind of trial, right?
Yeah.
So what is it that you get out of an array of data values for each? Or like, what is it that you get out of this?
So you're getting.
Do you have any information? So does it matter what order you specify, like sort of when you have a learning rate and stuff, and then you kind of use a little bit of the information you had before and then kind of builds, does that happen here too?
No, so basically here we are assuming that each trial is independent from the others.
Yeah.
And so here we have an array, but instead of putting simply one value, we're putting, again, assuming 3,000 samples, we are putting all the values of theta as a row, right? So it becomes de facto a matrix or an array of vectors. We're gonna get to the trial by trial dependency.
Okay, yeah, I would assume that that's a bit, at least if we talk cognition, that's maybe a bit of a realism. That these are gonna be completely.
Oh yeah, yeah. So in this specific experiment, people were told every time we're gonna change the error. But yes,
Okay, so the reason they updated the target when sending data.
Yeah.
Are you just like using Stan's inbuilt Bayesian mechanism
yes,
to simulate what's happening inside the participant set?
yes.
Okay,
And since everybody's gonna get the same stimuli, right? So since that is a fixed thing, the fact that we are adding a constant to the log posterior likelihood is not an issue. Because even if we're gonna fit different models, we're still adding the same constant to all of those. Good. Now, here, there is a simplistic assumption. People or their brain can optimally infer rate distributions. That's an assumption of the model, right? We could complexify the model and make it different. We're not going to do that now. Second, this is the simplest and most elegant code, and I have an anecdote that I'll share in a second. But it overloads your rows with all the thetas, right? So there are more elegant ways of coding. But this is just the most simple and elegant code that would fit on a slide. The anecdote is that I was coding this last week while I was at a conference. And of course, every time I have an idea of how it would work, it kept giving me some silly, oh, you're using the wrong type. Well, of course, the two vector stuff, I'm thinking. And then I wrote a mail to Malte and said, oh, Malte, do you have any idea on how to solve this? And as soon as I pressed send, it was, right, I'm just so stupid. It's the two vector. Then I fixed it and it didn't give me that error. And then I made it run. And of course, it wasn't working because I think I was trying to estimate the thetas in, I can't remember if it was in transform parameter or something like that. And then I wrote a mail to Mal and says, oh, sorry, that actually problem is solved, but now I get these errors. Do you have any idea where it comes from? And then I push send. And as soon as I push send, it was just, now I have the solution. Which of course it shows you that Malte can also work without working. Yes. Also, I hope that it, of course, I think that Josh calls it constructive vulnerability, showing your students that you're an idiot. But it should also sort of reassure you that making stupid errors while coding happens at all levels. Well, maybe there is people that don't do the same kind of constructive vulnerability that I have, but yes. Okay. You had a question? Yes, give me a question.
So data.
Yes.
If they don't want to go to our parameters, but it doesn't seem like they bias.
Is a parameter? What do you mean?
They got one, they got two, like there's something to be said.
Well, so bias, weight 1 and weight 2 are more traditional kinds of parameters that we're going to estimate from the data.
Yeah.
Right. Now I haven't done the full data simulation because I just wanted to show you how to play with the Stan code. But of course we would have real data, right? And then given the real data, we can estimate the bias, the weight 1 and the weight 2.
Yes, again, the 1 and 2 are not parameters. Okay. We just use state sampler to generate.
I think I'm gonna, I don't want to confuse you anymore, but technically they are parameters. Because they are unobserved that you're estimating from observed data, but they are different kind of parameters.
Yes, because it's a listed parameters, right?
Yeah.
You have 2 out of 8 of it.
Yes.
And the distribution, the distribution is going to be exactly that.
Almost exactly, but since it's a probabilistic, it's the Quinn mobile is traveling around in a random fashion. Yeah, very similar.
Yeah.
And if you have infinite samples, it's going to be the same.
Yeah.
Sorry, sorry to dwell on this. It just struck me like, can this model distinguish between the weight and the theta? Like, are they not going to be very correlated when you get out?
The theta, in a sense, is deterministic. Because the theta is simply determined by source 1, which is observed, and 8. So no matter how much, so the participant might then use that information to shape very strongly their behavior, to shape very weakly their behavior, or to shape not at all their behavior. And that's what will feed into weight 1. So the 2 sources of information are not.
I think maybe it's because I can't read the red. Like, is it?
It's a binomial logit LPMF.
Okay.
So here we're just abusing the sampler in a sense to say reconstruct that underlying distribution. But it is estimated, but you could have used in R, I don't know, D binomial. Right. And then the proper estimation, they're both estimation processes, but the real estimation as we've been doing it so far is only down here. But I know it's a bit confusing, and that's why I thought that we could spend some time doing these changes in the models, because the software is very flexible and we can think in very flexible ways if we start playing around with that. Mina, you have a skeptical face.
Yeah, no. I need to, it needs to sink in.
Yeah. Okay.
I tend to.
Now we have temporal Bayes. Right. So the idea is that so far as lots of experimentalists want to do, right? They try to eliminate the things that don't fit an ANOVA, thanks to very careful experimental design. And that's why basically in the previous experiment, at every trial, people were presented with a different error. So what happens since then? If we resemble something in which so we approach a situation in which there is learning, or a situation that is more close to typical Bayesian approaches, where the 2 sources of information are what you knew previously and what you're experiencing right now, right? And so for simplicity, we could have 2 sources of information plus the past, but I'm going to stick to the past and the current. So we'll take a kind of experiment that often is called the jumping to conclusion experiment. I'll explain why in a bit. There is an urn, and we sample n marbles from the urn, and we can then decide whether to spend 10 krona and sample again to get more information, or make a guess now. Does that make sense? It's called jumping to conclusion because there is a bias in the literature called jumping to conclusion that clinicians have been arguing that schizophrenics are prone to, in which even if you get a slight amount, very uncertain of evidence towards red, you might jump to red. Right? So in this scenario, there is only a source of external information at each moment, but previously estimated belief acts as an additional source. The previous posterior becomes, when you sample the second time, becomes the prior, right? The previous posterior becomes source of information number 1 or 2, whatever we call it. So now we have data where n is how many data points we have, just like before. We have y, that is whether the participant says red or green. We have new block that tells us whether the urn has been changed right after the participant has made a guess. And since I wanted to generalize, I put just marbles, so how many marbles were sampled as an additional information that we get in the data. So what we have is that parameter bias, the weight 1, the weight 2, and now we only estimating a theta 1, right? Because at each trial, we get samples from the outside only once. We don't have the others anymore, for simplicity. Then we have transform parameter, which is theta 2, which says that for each row in the data set, if we're starting a new block, the urn has just been replaced, or it's the first trial, theta 2 is equal to 0. Right? On a logit scale, it contains no information. We have no idea from before, right? We could make that into a parameter, but let's keep things simple. If this is the follow-up sampling, theta 2 is equal to our usual formula, bias plus weight 1 times theta 1 plus weight 2 times theta 2 in the previous round. Right? The combined information from the previous round. Does it make sense? Then in the model, we have priors for bias, priors for W1, priors for W2. We have our estimation of theta 1 from source 1 and marbles. And then we have that our choice of red or green is given by bias plus weight 1 times 2 vector theta 1 plus W2 times 2 vector theta 2. Right, and right now, I'm only modeling whether the participant is saying whether it's red or green. And we are assuming that the participant will register the red or green belief, even if they decide to keep on sampling. Because I'm going to add complexity only in the next slides. Right now, what I just want you to focus on is the fact that in the transform parameters, right, we are generating the posterior and saving so that it can become in the next round one of the two sources. Does that make sense? Lara, does that start answering your learning? Yes. Yeah. And then there's something there on the generated quantities, but just so you have a reference there. We can diagnose it. It's all fine. We can do the prior posterior updates. It's all fine, just so you don't remember. You don't forget all this stuff. We can plot the bias against W1, the bias against W2, the W1 against W2. What do you see there? I see pine cones. So what we see is that the posteriors are shaped a bit like funnels. The model is not finding problems here, but I would bet 100 krona that if we made this into a multi-level version, we would get issues, right? But at least now we know and we're prepared. Okay, here I didn't prepare it, but if we starting to do these kind of things, right? As we did once we were playing with reinforcement learning, we might want to figure out good ways of representing the model behavior. And just like in reinforcement learning, it might be, I haven't done it because I didn't have time. I was hoping I could be distracted a bit during the administrative 9 to 2 meetings today, but I was one of the two organizers, so that was hard to pull off. But you could actually visualize how the belief that is source 2 is updated throughout the run of a sequence of sampling. Right? That would be a good way to test what happens given your priors on a meaningful behavior and what happens after you fitted the model, blah, blah. Okay, but now we assume that we had choices that the participant was registering whether they would have betted red or green at every single trial, no matter whether they sample again or not. But the true experiments are actually not asking to register a choice unless they stop sampling. So how would we play with that? So it's the same as before, but now we are looping through every row of the data set, and only if the choice is equal 1, meaning we're not keeping on sampling, but we're making a choice. That's a new variable. 0, keep on sampling. 1, now I want to bet. We estimate bias W1 and W2 given the actual red or green choice of the participant, right? The theta 1 and the theta 2. So basically, we're filtering out only those trials. Does that make sense? What's puzzling you?
I think it's just a choice
Yeah.
equal to 1.
Yeah, so now we have Y, it's still whether they've chosen red or green, but choice is a new variable that at every sampling, they get told, do you want to make a choice or do you want to keep on sampling and pay
People
that
are
for
asked to continue until they feel confident.
Exactly. Or you make it economic, so you don't ask them to wait until they feel confident. They just know that every time that they keep on sampling, they lose some money. Right? You can implement these in many different ways. Yeah. Of course, one could tell me, well, Ricardo, why didn't you just aggregate all the sampling trials so that you count how many marbles are red out of all that were sampled? Does that make sense? Right? Why do you go all the bother to do the trial by trial update if you're really only going to model 1 out of 4 trials? Does that make sense? As a question? Okay, so basically what we're doing here is we build a full machine that on a sampling to sampling base updates the belief, this estimated belief of the participant, given what happened in the previous trial and what gets sampled now. But we calculated the log posterior likelihood only in the trials in which they actually make the choice. So a more economic way of modeling this would simply to say, if there are 3 trials in which people are sampling, let's just count how many marbles they sample in total in those 3 trials, how many are red, and then we use those 2 variables to estimate the underlying probability of picking red given a bias and a weight 1. And I go through these process not only to make your life hard or to pedagogically show you how to change the weight, but also because we can have a model that has 2 outcomes. That in some trials, it has the choice whether to keep sampling or not. And in other trials, it has both the choice of stopping to sample and which choice is given. Right? Instead, in these models, we can put multiple outcomes. Right? We don't need to just do the usual GLM thing where we only estimating, given one y and a bunch of x's, what are the coefficients, values, distributions. We can actually say, here we have 2 outcomes, whether to keep on sampling, and when you stop sampling, whether it's red or green. And these, again, with a warning, because I haven't stress test the model, it compiles, it fits on some random data that I put in, but I haven't really checked whether it makes a lot of sense. But this is how I would go at modeling. So we have n, that's the number of rows in the data set. That's an array of length n where we have the color choice, which is 0 if it's green, red, 1 if it's red, and actually, I think I need to put, I cannot put NAs. I would have wanted to put NA. Conceptually, we would put NAs when a choice is not made, but we cannot, so we can just keep the previous choice. We'll just make sure not to look at it. Or we could put 3, just so that it crashes if by chance it looks like that. Then we would have new block just before, like whether it has started again. We have sources 1 and we have marbles 1. The parameters, now I remove bias so it could stay in one screenshot. W1, W2, and theta 1. The transform parameter is the theta 2 that gets updated on a trial by trial basis. That's the posterior that becomes a prior when we keep on sampling. And then the model as first the 3 priors, the 2 priors for W1 and W2, then the estimation of theta 1 given source 1 and the marbles, and then a full model for all the trials where sampling choice is determined by sum, which is how far we are from 0. Because we will stop sampling when we get far away enough from a state of uncertainty, 0. Right? The further we are from our initial, we have no idea whether it's green or red, the more likely we are to stop sampling. And then, only for those rows in which sampling choice is equal 1, we have a model that estimates the color choice as a function of W1 times theta 1 plus W2 times theta 2. And I know all of these is a mouthful, mindful, brainful, something, right? But it's just to show that once you start to think in a generative fashion, as we've been doing throughout this course, all sort of fun setups are possible, just be reminded that you will have to write a few emails about it in order to push send and then know what the problem is, right? Does it make sense? It doesn't need to make perfect sense, but the general idea, does it make sense? That you can actually have two outcomes, and one of these two outcomes is only in some rows. Ain't it cool? All the stuff you didn't know you needed. Okay, there's several alternatives, but we can't really go through that. And can I do this? Yeah. What if actually so we have weights that are fixed, right? We are saying in our models that certain people trust evidence from their own hand more than what they trust evidence from other people, for instance. But especially in a context where we can see what the truth would be, right? We make a guess and we get a feedback. We can actually learn how reliable our guesses are and how reliable English guesses are, right? So we can adjust how much weight we put on these sources on a trial by trial basis. Does that make sense? The idea? Good. I know it's late. And we have the weighted Bayes model simplified, so we don't need to spend time on bias. And we learn a different model, reinforcement learning. Nothing stops us from adjusting the weights according to our reinforcement learning procedure. There's very many. I played with at least 3 different ways of doing that. All of them compile. I haven't stress tested them completely, but I'm just going to present one of them, right? The idea is that if the other was right, given feedback, we increase W2. If the other was not right, given feedback, we decrease W2, all according to the delta rule. If the other is always right, we should follow what the other is doing, right? We should put a weight that is 1. We should take it at face value. If the other is always wrong, we should put the weight at 0 so that we ignore. Well, actually, we could do the opposite, but if the other is a chance level, we should put a 0 there. Here is just a snippet of the same code. Right? But these, again, what we can do, right? We can say that if we're not at the last round, because if we're at the last round, we don't need to update stuff. Right? The weight W2 can be updated according to the delta. And blah, blah, blah. There is a paper where they go through a few different alternative models on how to do that. Social learning through associative processes at computational theory. But also, I just wanted to say that you don't need to actually necessarily put together reinforcement learning and weighted Bayes just because it's the one that you know. But it was fun to play with both of them since it's the ones you know. And now there's no time for questions, but I'll see you tomorrow for finalizing or doing the last important week on the portfolio, unless I get feedback that more time is needed. We'll talk about that tomorrow. And then next week, we'll start a whole new set of models that are important in this literature, which is models of categorization. And we'll start with a game. Woo! So thanks.